start with the conference. We have speakers from 22 universities from 9 countries. And our first speaker today is Anna. Can you put on her slide? She already finished her PhD in late 2018, but she's already an assistant professor since last year. Congratulations. In Chieti-Pescara. And her talk is
non ci sta riuscendo.
It's about non-universal fluctuations of the empirical measure for isotropic stationary fields. Here you get the mic. I hope it works.
Thank you. Okay, is it working? Yes. Okay. So maybe I should get off the mask. So is it possible?
Yes.
Okay. So first of all, I would like to thank the organizer for giving me the opportunity to come here in this nice place and to give a talk, of course. And also, I'm very happy to finally be able to attend a conference in person, because it was a long time without conference in person, and I was missing them a lot. So, as Michael already said, today I'm talking about a work which is titled Non-Universal Fluctuation of the Empirical Measure, or Excursion area, for isotropic stationary fields on the two-dimensional unit sphere times the real line, R. And this is a joint work with Domenico Marinucci from University of Rome Tor and Maurizia Rossi from University of Milano Bicocca. And this work you probably will see, hopefully, very recently on the Annals of Applied Probability. So the field, my field of interest is probability. Okay. So since it's a conference about mathematicians in, let's say, applied sciences, I wanted to start with a slide on the possible application of spherical models. So the first field of application is Cosmology. The sphere in this case represents the universe as seen from the Earth. So you need to imagine the sphere as the universe seen from, let's say, from the center of the Earth, in some sense, okay? And a book, a reference book that is very much used in this field, like astrostatistics and cosmology, is the one by Domenico Marinucci and Giovanni Peccati. It's from 2011, and its title is Random Fields on the Sphere, Representation, Limit Theorems, and Cosmological Applications. The other field that uses spherical models is geophysics, in which, of course, the sphere represents just the Earth. And a reference that I wanted to show you is the book by Christakos, which is titled Random Field Models in Earth Sciences. And finally, another important application is on medical imaging, in which the sphere usually represents the human brain. And I just put a reference paper because I couldn't find a book, but there are many papers in the literature about this kind of applications. And its title is basically on brain mapping, okay? So actually this is the only slide on application, because what I do is quite, what I do theoretically, practically in mathematics is quite theoretical, so yeah, I'm sorry, I hope that the audience will enjoy anyway the talk, but it won't be so So applied. So let me start with the model that we consider. So we consider a random field, which is just a random function defined on a probability space, omega fp, which we assume to be Gaussian. And this field, this function, is indexed by a point on the sphere, x in S2, so the unit sphere of dimension 2, and a point t on the real line, r. So what you need to imagine is that we have the evolution of this function over time, and this function moves, take value from the sphere, okay, on the sphere. And in particular, we are interested in some geometric quantity related to this field. So we are interested on the excursion set of this field at a fixed time t. So we fix t in R, and we consider the region over the sphere in which the function is above a fixed level in R. Here I make these simple drawings in which basically in my mind the darkest region are the one above the level u, and the clear region are the one under the level u. Okay. So of course we need to put some condition on this field. So the first condition is that the field, this random field, is centered. This means that the mean of the field at each point x and time t is equal to 0. This is actually a condition that from which we don't lose any generality, so one can always rescale by the mean the field. The second assumption is the most important one, and is the one is also on the title of this talk. So this field, this random function, is isotropic and stationary, so isotropic in space and stationary in time. This can be seen from the covariance function of the process of the field. So this covariance function is depend on the inner product between x and y. So the inner product on R3, which is just the cosine of the spherical distance between x and y, and the difference between the times t and s. So the stationarity, you can see it from t minus s, and the isotropy from the inner product, the fact that the gamma depends on the inner product. This gamma must be a positive semi-definite function. Finally, we will assume also that gamma is continuous, and this means that z, the field z, is mean square continuous. Okay, those are the conditions. Can I use this water? Sorry, I forgot.
Yes, of course.
Yeah,
Great.
Okay, sorry. So these are the conditions on the field. Under this condition, the field has this, let me say, nice representation, which is just a Fourier expansion of the field over the orthonormal base of the so-called spherical harmonics. These spherical harmonics are an orthonormal base, as I said, on L2, S2, and are deterministic functions. So the random part of the field, you can see it, everything on the coefficients, so the Fourier coefficient of these expansions. And in particular, we will call ZL as this component of the series, okay, which are just the sum over m between minus L and L, of this random coefficient, which depends on the time L, and this deterministic function, which is a spherical harmonic, so order Ln. Okay. Under this condition, as I said, we have this nice representation. L will be called unmultiple, okay, And we have that these ALM are a family of stationary Gaussian processes that are independent in the sense that so the process ALM is independent of the process AL prime M prime whenever L is different from L prime or M is different from M prime. In particular, moreover, we have that the gamma, which is the covariance function that we introduced here, can be also expanded as this series, where we have basically the temporal covariance and the space covariance. So the temporal covariance is just is given by the covariance of the covariance function of the process ALM, and this PL is just the Legendre polynomial of order L in the inner product X and Y. So this is, one of the crucial tools for studying these models. This nice representation, and this is, heavily depend on the fact that we chose the model to be isotropic and stationary. Otherwise, this wouldn't work, of course. So now I give you like the condition on the field, the representation on the field. I need another important assumption, let's say. So I need to introduce the temporal part of the model. So how does the covariance of these processes ALM behaves? So this covariance function CL tau is, let's say, asymptotically equals as tau grows to infinity to CL0 times a function that depends on a parameter that we will call beta L. And this family of function has the following form. So if beta L is between 0 and 1, it takes this form of 1 over 1 plus the absolute value of tau to the power beta L. And in the case that beta L is equal to 1, it takes the form of 1 over 1 plus the absolute value of tau to the power alpha. I'm reading everything because I believe that very far maybe one cannot see very well what I've written. But anyway, so where alpha is some parameter between 2 and plus infinity. In particular, this kind of assumption is very general because it covers most of the stationary models in time. And in particular, we will say that the ALM process is long memory whenever beta L is between 0 and 1 because this corresponds to the fact that the covariance function CL is non-integrable. And this non-integrability, one can see it as like the memory of the process decay too slow, so that this function is indeed non-integrable. In the other case, we will say that the process is short memory because the covariance is integrable and then the memory decays fast enough. Okay. So now I introduce the model, so we can move to what interests us in the model. So there's another slide. So now I wanted to say also this. So these are other assumptions that are needed in order to state our main results. So as I said, in this model for the temporal covariance, what counts basically is this memory parameter, okay? And indeed we will call it memory parameter, and we will assume that there exists on the old. You remember that we have this expansion with these multiples L that goes from 0 to plus infinity. We will assume that if we take the minimum of the memory parameter on all the multiples, then this minimum exists, and we will call it beta L star. Okay. We exclude from this minimization the parameter that correspond to the zero multiple. This is because the zero multiple somehow represent the trivial case, but this we will see later. So the smallest exponent, of course, corresponds to the largest memory for what we were saying before. And so we will define also I star to be the set of multiples for which the memory parameter achieve the minimum. And then basically these multiples from the expansion represent the one with the largest memory, and so the one that somehow contribute most to the covariance function of the model. So now, yes, finally we can introduce what we are interested in. So we are interested in this random functional, which is defined starting. Is it working?
Nope.
Okay, sorry, because I cannot recognize when it's working. Maybe. For me, it's so I was saying, it's, what we are interested in is this random functional that is defined starting from the area of the excursion sets that we introduced before. So we are basically interested in the area of this at a fixed time t of the darker region, the darkest region of the small drawings that I've done. And in particular, the expectation of this area does not depend on t, so it's equal to 4 pi times 1 minus phi u, where phi u is the cumulative distribution function of a standard Gaussian random variable. And starting from this area at fixed time t, we will define this functional, this random functional, which is just that we call capital M t u, and it is just the integral between 0 and t, where t is greater than 0, of the area at time t above the level u, the fixed level u, minus its expectation integrated over t. And we are interested basically in the fluctuation of this random functional as its capital T grows to infinity. So, so now I'm in the position to state the main results of this work. So we need to, in order to state our result, to introduce this, to define this MTU with a tilde above. This is just the standardized version of the random functional, which is so the random functional over the square root of the variance, of its variance. And we will see that basically all the results that we will see are governed by an interplay between the beta 0, which is the memory parameter of the 0 multiple, beta L star, which is the smallest memory parameter of the expansion, and the threshold level u. So in the case of short memory, the result is quite simple to state, you could say. So we have that basically the threshold, so u does not affect the result, and we have that if u is different from 0, beta 0 equals 1 and 2 beta star is greater than 1, or u equals 0, beta 0 equals 1 and 3 beta star is greater than 1, then the variance of our random functional is of the order t, capital T, and the limit of the standardized functional is Gaussian. standard version. Okay, so this is the case of short memory. For the long memory situation, so the computation gets a bit more involved. We have so we have a first long memory situation in which basically we can say it's the trivial long memory situation in which the smallest memory parameter is given by beta 0, so the 0 multiple, and in this case, again, the level does not affect the results. So we have that if u is different from 0 and beta 0 is less than the minimum between 2 beta star and 1, or u equals 0 and beta 0 is less than the minimum between 3 beta star and 1, then the variance is of the order t to the power 2 minus beta 0, and the limit is Gaussian. Now, in this other long memory situation, we have that finally the level, threshold level affects the result, both of the variance and the limit distribution. So we have that in the case of 2 beta star less than the minimum between beta 0 and 1, then the variance is of this order, t to the power 2 minus 2 beta star, and the limit is non-Gaussian. We will see in detail what it is. And for u equals 0, we have that if 3 beta star is less than the minimum between beta 0 and 1, then the variance is of this order, t to the power 2 minus 3 beta star, and the limit is again non-Gaussian, but it's a different limit. We'll see it later. The one for the variance with the logarithm are the, let me say, the boundary cases of the variance, so see them. So I just wanted to say a few words about what is this Bayes cancellation. Actually, it's something that is, I mean, many researchers are interested in this Bayes cancellation, which is basically something that happens in this kind of geometrical functional. In particular, that what we observe often is that the order of the variance gets smaller from the level u different from 0 to the level u equals 0. And I just wanted to, maybe some of you know about it, but it's also here we have a kind of Bayes cancellation phenomenon for the long memory framework, in the sense that for u is different from 0, we have this rate of the variance. As soon as we move to u equals 0, we have that the rate gets smaller, and in particular we have these three possible situations. Okay, this is just a few words about it. So I just wanted to move to a sketch of the proof, just to let you see what are the main tools that we use in this field of research. So what is very much used is the so-called chaotic decomposition of the functional. What is this chaotic decomposition is basically we expand the functional in the series of its projection to the linear causes. So we have this functional MTU that is an explicit functional of a Gaussian function, and it's of finite variance for each capital T. And this permits us to basically expand it in this nice series in which we know explicitly the components, which are just these, let me say, simple integrals, in the sense that basically one can explicitly work with them in computations. So we have that the projection of the functional onto the qth order linear cause is just equal to this coefficient, which is just the Hermite polynomial of order q minus 1 in the threshold level u. times phi u, which is the standard density function, the density function of standard Gaussian random variable in the level u over q factorial times the integral between 0 and t times the integral on the unit sphere S2 of the Hermite polynomial of order q in the random function z xt integrated over x and t. So, but what are these linear causes that are basically the crucial tool of the proof of these results? So let me say just a few words about these linear causes. These are just how these are constructed. So these are constructed like starting from the field. As soon as you have a Gaussian field, you can construct basically the linear cause. And so we call A the closure of the linear space spanned by these processes ALM. And then we fix a Q in N0, so N included 0. And we consider the closure of the linear space generated by the product of these Hermite polynomials. These Hermite polynomials are of order P1, Pk, and the sum of the Pi's must be equal to Q. And they are evaluated in this C1, Ck, which are standard Gaussian, which are taken from the space A. And basically what one can see is that these CQs, which are, so this CQ is the Qth order linear chaos, so these CQs are orthogonal to each other, and then so the space LQ of this probability space can be written as this direct sum. And that's why basically the functional, a functional f in this space can be written as a sum of the projection onto these spaces. And in particular, what is important is that if the variance of the functional, so f, you need to imagine that it's our functional here, MTU, sorry, this one. Okay, the variance of the functional can be written as the sum of the variance of the terms of the expansions. Okay, so let me show you how these causes are treated somehow. So we have that since the functional is centered, the zero cause is 0. So we start from the first cause. So the first cause is just the integral of the field. So that's why it's just the integral of the empirical mean of zt. And so it's, of course, Gaussian for each t, because it's just a linear transformation of a Gaussian. Okay? And the variance can be easily computed as follows. In particular, we have two possibilities for the variance. If beta 0 is equal to 1, the variance is of the order t. Otherwise, if beta 0 is between 0 and 1, then the variance is of the order t to the power 2 minus beta 0. And this, if you remember a bit the slide on the main results, basically, when beta 0 is between 0 and 1 and we have this condition, then basically the first linear cause is the one then that contributes most to the variance, since the variance can be written as the sum of the variance of the chaoses. So it's the one that contributes most, and this in probability means that basically the behavior of our functional of interest is completely determined only by the first chaos. So this means that we simplified somehow the entire functional with just this simple integral. So the behavior of the entire functional, we can understand it only studying the first chaos. So if we move to the second chaos, of course the higher the chaos is, the more difficult are the computations. And for the second chaos, so they are still quite easy. So we have that the second chaos has this form, which is just the second Hermite polynomial of the field. And then we can compute the variance of the second order linear chaos using the so-called diagram formula that basically let us write this variance as the integral of the covariance function of the underlying model zxt to the power 2. The power, of course, is related to the number of the chaos. And thanks to this fact, to the diagram formula, we need just to compute this integral. And basically, what we obtain is that the variance of the second chaos is of this order, t to the power 2 minus 2 beta star. And in particular, its rate, it's completely determined only by the multiples with the largest memory. If you remember what I star was, this is the set of the multiples with the largest memory, and those are the ones that determine the behavior of the second chaos. But not only this, basically under this condition, what happens is that the second chaos completely determines the behavior of our functional of interest, the entire functional. And hence, by knowing to what distribution the second chaos converge, we know what is the limit distribution of the functional, the entire functional. And this is the limit is given by a composite Rosenblatt, and which is just a linear combination of a Rosenblatt distribution, which is a known distribution in probability. So regarding the higher chaoses, again we use the diagram formula. So we get that the variance of the qth order linear chaos is given by the variance, the covariance function of the underlying field to the power q now, because we have the q chaos. And continuing with computation, we get basically this integral in which you can see again the covariance is related to the temporal process ALM. And so again, the variance of the qth order linear chaos is completely determined by the multiples with the largest memory, and in particular is of the rate t to the power 2 minus q beta star. And whenever u equals 0, the chaos that basically determine the behavior of our functional of interest MTU is the third one. In particular because the second chaos vanish for u equals 0. And what we have in the limit is a so-called higher order composite Rosenblatt, which is just again a linear combination of somehow higher order Rosenblatt. It's a quite involved distribution, so actually it's not really interesting to know the limit, but anyway, we know that it's non-Gaussian and it's different from the previous one. Okay, now I give you a summary of what I have said, so maybe some of you can a bit understand. I know it's a bit involved. So what do we have here? So when does the first chaos dominates our functional? It happens whenever u is different from 0 and beta 0 satisfies this condition, and then the variance is of the order t to the power 2 minus beta 0. Otherwise, when u equals 0 and satisfies this condition, and the variance doesn't change. So it's not affected by the level. In this case, the limit is Gaussian, of course, because the first case is Gaussian. So the limit, of course, is Gaussian. Regarding the second case, so this dominates the chaotic expansion whenever 2 beta star is less than the minimum between beta 0 and 1, in case u is different from 0, and the variance is of the order t to the power 2 minus 2 beta star. However, it can never dominate when u equals 0 because it vanishes. And in this case, the limiting distribution is non-Gaussian. The third chaos never dominates whenever u is different from 0 because either dominates the second chaos or dominate all cases. But it can dominate the series whenever u equals 0 and we have these conditions. And the limit is non-Gaussian again, but it's different from the other non-Gaussian limit. When do all chaotic components determine the behavior of the functional? This happens in the short memory case. So whenever beta 0 equals 1 and 2 beta star is greater than 1, or when beta 0 equals 1 and 3 beta star is greater than 1 in case u equals 0. The variance is of the order t and the limit is Gaussian. So let me make some comments about what we have seen. So this kind of phase transition that we have seen in the results are basically related to this diagram formula that says us that the covariance between two Hermite polynomials of the same order in two different points of the field is equal to a constant times the covariance of the underlying field to the power q. And so in the case of long memory, the non-summability of the covariance basically permits to have a kind of permits to a single chaotic component to dominate the series because if we elevate the covariance to the power q, there must exist a q such that the covariance becomes summable, and hence basically at some point the higher cases do not contribute anymore to the variance. In the case of short memory, we cannot have this phenomenon because the summable covariance stays summable basically. And so all the cases contribute to the asymptotic behavior of the functional. So I hope it was clear enough, and I thank you for your attention.
So let's hear from the floor. There is any question? Mickey will go.
I actually have two. So the first one is a very small one, directly at the beginning when you said the applications. Are like climate and weather models also an application?
Yes.
Because it's,
yes.
Okay, it's also used there.
Yeah.
Okay.
So I let's say grouped it in earth sciences, but
Of course, I assume that.
Yes.
And on your last slide, can you show it again? Just like for someone who's totally not from the field, which is me, is there some intuitive answer why the higher cases do not contribute? Like, we saw a mathematical reason, but is there some intuition behind it? Hello?
Unfortunately, I think I don't have. I believe that sometimes there is not always an intuitive
Yes,
answer.
of course.
Sometimes
Yes,
it's just a computation that gives you nice results, but so this I cannot answer. Basically, for me, the intuition is the use of this diagram formula that I said. So it's like a bit computational as answer. But,
Okay, if there is not any question, okay, I will ask one then.
You had at a certain point when you did your representation, right, and you divide it into multiple.
Yes.
This reminds me something that is very often done in geophysics model, and this is the use of empirically orthogonal function, right? Is there any kind of relationship between the empirical orthogonal function that are used in geophysics?
So I don't know this tool that you mentioned. Probably there is. I don't know if it's
very
if you
similar
use the
to
spherical harmonics. So if you use the spherical harmonics, probably it's just the same. I think that there are also like a kind of generalization of spherical harmonics to situation in which the field, for instance, is non-isotropic. But I don't know much about it, but I'm sure that there are several generalizations of this kind of representation. This is somehow, let me say, the simplest one because you have all the nice properties, isotropic, IsotropicStationary, but it often it's not the case, of course. So I don't know, maybe in geophysics they use also more involved situations somehow.
Thank you very much.
Okay.